Hello, everybody. Thank you very much to all the viewers for being here one more year at the OpenNebula Con. During this session, we are going to discuss the automating apps deployment with OpenNebula and Terraform. My name is Victor Palma, cloud engineer at OpenNebula, and joining me today is Dan Cazacu, a senior reliability engineer from Proton, which will show us a real case of automate automation using OpenNebula and existing integrations such as Terraform. So first, let us start with an introduction to get some context. First, what is infrastructure as a code, or IAC? This is fundamental principle in modern DevOps practices. So AIC allows us to manage and provision computing infrastructure through machine-readable configuration files, rather than through physical hardware configuration or interactive configuration tools. AIC brings several key benefits such as consistency and automation. We will discuss all these benefits in the next slide, but first I would like to mention the more relevant tools with which OpenNebula integrates. We have first the OpenNebula Terraform provider. This tool allows automatic resource creation, making it easier to manage your infrastructure. And then we have the OpenNebula Deploy or OneDeploy that facilitates the automatic deployment of clouds, helping to streamline the setup of complex environments through Ansible playbooks. You can see here both repositories, or both of them are public, so I encourage you I encourage you to participate in both of them. So let's dive into some specific use cases where IAC and the best practice with OpenNebula really shine. First, we have the environment parity, that ensuring that all the environments, that means development, testing, staging, production, have an identical configurations. This practice avoids the notorious "it works on my machines" problem by maintaining consistency across all stages of development and deployment. Then, secondly, we have the on-demand resource allocation. Resources can be dynamically allocated based on current needs. This flexibility is vital for handling varying loads, especially during peak times. OpenNebula supports deployments not just on-premise, but also in public clouds and at the edge, providing a unique flexibility. Third, we have the automate testing. Automate testing is another significant advantage. So you can automatically provision environments specifically for running tests, ensuring that tests are conducted in isolated and controlled setups. This can be easily integrated with CI/CD tools like, for example, Jenkins and GitLab CI, allowing for continuous integration and continuous delivery. Finally, we have experimentation and innovation. So thanks to that, you can quickly setting up sandbox environments for experimentation that allow you to your teams to innovate without the risk of affecting production systems. This enables quick prototyping of new features and services, fostering a culture of innovation and agility within your organization. And that's very cool. So now let's take a closer look at the OpenNebula Terraform provider. This provider is designed to interact with, with OpenNebula resources, enabling you to manage these resources using the IEC principles. So how it works? Well, as you can see in this diagram, the provider uses the Go OpenNebula Cloud API library to communicate with the OpenNebula core through the XML RPC API. This library is crucial for executing automatic action within your OpenNebula environment. For full documentation and more detailed information, you can visit the provider documentation that you can see here in the slide, registry.terraform.io providers OpenNebula. This provider simplifies the management of OpenNebula clusters, making it easier to automate infrastructure tasks and integrate them into your DevOps workflows. So let's talk about now about how to set up Terraform for OpenNebula. You need a few of prerequisites. First, you need Terraform installed on your host machine. This is the primary tool that will be running the configuration files. And then you need access to an OpenNebula instance endpoint. By default, is the port 2633, but you need to review that in your OpenNebula configuration. Here is an example configuration for the provider. This configuration does a few things, like, for example, it specifies the required provider, in this case OpenNebula, and the version to use, and it configures the provider with the endpoint, username, and password necessary to connect to your OpenNebula instance. This setup is essential for Terraform to interact with OpenNebula and manage your infrastructure, so um, it's necessary to have all of this configured, like you can see here in the slide. Next, let's look at this practical example of deploying virtual machines using Terraform with OpenNebula. First, you can see here that we define the resource for the host. This configuration creates a KVM host with a specific CPU and memory over commitment settings. The tag session that you can see at the bottom uh, as metadata to the resource, which can be useful for identification and management inside OpenNebula. Next, we can define the VM. This resource configuration specifies a VM with a given name, template ID, CPU, virtual CPU, and memory allocation. Tags are again used for metadata. Once these resources are defined, you can run the usual Terraform commands, Terraform init to initialize the configuration, Terraform plan to see what changes will be made, and Terraform apply to run the configuration and create the resources. The OpenNebula Terraform providers, of course, support a broad range of resources, making it a versatile tool for managing your infrastructure. Some of the key resources include hosts, that means physical or virtual machines that provide computer resources, data storage for storage system and VMs and templates, virtual machines, user and groups, marketplaces that are repositories for application image and templates, networks for interconnecting virtual machines, virtual routers for routing traffic between networks, templates that are the blueprints for the VMs, and much more, such as ACLs, configurations, virtual data center, or cluster provisioning. Each resource type has specific configurations and attributes. For detailed information on each resource, please refer to the provider documentation. I would also like to take this slide to encourage you to participate in the OpenNebula forum. OpenNebula has an active community where you can share and learn in community about the open source cloud. Don't miss the opportunity to register if you haven't done it yet and join to a community in continuous sessions. Having said that, I will pass the torch to Dan, who is going to tell us how he takes everything we have seen to a real example.
Hello, Victor. Good afternoon. Thanks for having me here. It's a real pleasure to be part of this event. And I would like to take a few moments to say thank you for your wonderful job on the provider. Me being here without it wouldn't be possible. So thank you and your team for doing so. Okay, so let's get started. My name is Dan Cazacu. I'm a senior site reliability engineer at Proton, and I'm responsible for managing Proton's self-service on-prem cloud provider infrastructure. This infrastructure is based on OpenNebula, as you have already deducted. And we chose OpenNebula for a couple of reasons. One of it was being efficient storage allocation. In Proton, we had this issue a while back with managing storage resources. Basically, we try to lower costs by removing NAS storage and try to use local storage for our deployments. And OpenNebula helped us a lot with that because it has a lot of drivers that allows you to customize your storage needs. There are a bunch of predefined ones like the NASs, the local storages, the OpenStore, the Ceph ones. But even if you go with the default one, there are also more options that allow you to customize it. So we use more than the local one. We also use a combination of storage drivers, but the customization that allows you to do it was a really huge benefit for us. So that was one aspect. The second one is the automatic VM deployments, because it had the Terraform provider that Victor was talking about a few moments ago available. So that allowed us to do infrastructure as code, because what is an infrastructure if you cannot see what's going on inside it? So infrastructure as code was really important for us. That way we could deploy a huge number of VMs at any moment, at any time, in any site without any issues. And lastly, and not one of the most important aspects, was that it was cost effective. The licensing that OpenNebula provided was really beneficial, really benefit for us. It, if I'm not mistaken, is under Apache 2.0. That was real helpful. Okay, so this is like a quick introduction about the tool. Let's have a look at the tools that we used to automate our VM deployments. So first of all, Terraform, as you know it, had a couple of issues with licensing recently, but still a great tool. Terraform allowed us to connect via the provider to the OpenNebula API, and that way all the OpenNebula resources that Victor was talking about earlier became available in EIC. On top of Terraform, we are using TerraGrant, which allowed us to avoid repeating our code. It allows you to do multiple state locks. It allows you to reuse your modules in the same time, and it has a lot of beneficial functions that we could use. One thing that I didn't mention is that you can take the provider that OpenNebula grants you, and you can repack it yourself into your own module, which is actually what we did. This is one of the main reasons that we come with TerraGrant on top of it. You can repack it and deploy it in a concurrent way, in a number of ways, like in every site available in the same time. Its possibility, it's basically endless. These two automation tools wouldn't be possible without Atlantis. Atlantis is the glue for those two. It automatically pulls your requests and runs them for you. Basically, you don't have to do anything. You just tell Atlantis to build your plan, and that's it. It will do it for you. We'll go into technicalities a little bit later. GitLab, of course, one of the next great tools that we use. It allowed us to use ACLs for our repositories and our plans, and it allowed developers to use a self-service platform. Basically, every developer can come in and do a merge request, get approval, and raise a VM by themselves in a couple of minutes. That's one of the main features that we strive for to encourage self-service. That way we reduce deployment times and you don't have to go around and chase for new VMs and so on. Of course, OpenNebula, without it, this entire deployment wouldn't be possible. And Netbox, which is a centralized source of truth for network infrastructure. All the resources are synchronized together around Netbox. It's an amazing tool. I highly recommend it if you haven't used it in your infrastructure until now. It allows you to verify for available network resources and what you can allocate to your new or existing virtual machines. Of course, it doesn't stop there. It can also keep an inventory, sort of say, for any object that you create in OpenNebula. So let's talk a little bit about the architecture. I think everybody is familiar with the OpenNebula front end. It's an amazing tool. It allows you to connect to a number of virtualization solutions. One of them is KVM. As far as I know, it doesn't have a restriction for number of KVM nodes that you can add into a front end, but of course, I don't think you should add too many. And it will orchestrate your VM deployment into your KVM hosts. You can either group your KVM hosts by clusters, or you can use them individually. It's completely up to you how you want to use them and how you organize your underlying network infrastructure. So the way the flow works is that basically a VM or a system admin or anybody in your infrastructure creates a new merge request. It will seek for approval. Once an approval is taken, GitLab will automatically fire a hook into Atlantis. Atlantis will run a plan for using Terraform for your upcoming changes. It will query Netbox for any available resources, and then it will apply those that plan via XML RPC into your OpenNebula frontend. Your OpenNebula frontend will deploy a VM to any available clusters or hosts that you have, and you'll have a bunch of VMs or one VM, depending how many you define, available in your infrastructure. This entire operation takes, I think, less than 30 seconds. It takes more to actually run the code, to write the code, than actually to run it. In the next slide, this one, having a short example of deployments that you can use in your infrastructure. Basically, this is a Terraform structure that you can use to set up your infrastructure. It contains a tenant, a group, and that's about it. You can organize your infrastructure according to your needs. This is just a basic rudimentary example. If you're using AWS, for example, you can organize it by tenants. If you use KVM, you organize it differently. It really does. It's really completely up to you. Okay. On the right side, you can see how TerraGrant ACL looks like. This is a short plan. It's a file that calls for a parent ACL. It will initialize a module, which will take as an input all the variables that you are given to. These variables are part of the in-house model that we designed. It's something that you can do as well. And it allows you to specify your cluster, your CPU model, your data store, image name, host names, and so on. The host names are actually the VMs. You can either use 1, 2, 3, or you can specify the number of VMs that you want to use. These are just a few optional variables, the data disk, for example, but the number of optional variables that we actually have in our infrastructure are over 50 variables. Okay, so after you have written your Terragrant ACL file, you'll push your merge request. You'll see Atlantis plan running, either automatically or manually, depends how you configure it. And then you'll have to seek for approval. Basically, this entire flow is explained here in this CI/CD flow. It's exactly what I was talking about earlier. The first developer does a git push. It will create a pull request. We have set up the plan manually. Basically, the user has to add a comment to it, Atlantis plan, and it will send via a GitLab or GitHub, depends up to you, API hook to Atlantis, which will further pull your merge request and return a plan to the user. This is done in real time in GitLab. If the plan is okay, you can seek for approval as soon as approval is given, or you cannot. The fact that you run GitLab, it's a huge advantage because it allows you to configure your ACLs how you want. So you can either configure your merges with reviews, or you can just skip this step. So this is more tied down to your organization and to your organizational needs. In our organization, we use the code reviews. Therefore, you have to seek a code review and then type Atlantis apply yourself after the review has been approved. GitLab will fire another hook to Atlantis in that point, which will perform a Terraform or Terragrant, depends on the repository that you are using. You can either use plain Terraform with the provider that Victor was talking about, or you can wrap it up with Terragrant if you have a large fleet that you want to deploy in the same time, and it will apply those changes to the OpenNebula API. Atlantis has this great feature that automatically merges your merge request into the master branch as soon as the Terraform apply has been completed. So this is a basic flow of a VM deployment. Anybody can do it using the presented tools, and by leveraging these tools, we ensure efficient, automated, and cost-effective management of our virtual infrastructure, enabling seamless operations and rapid scalability. Thank you.